In this example, we're given a two-bar linkage and directed to find two things. The first is the angular speed of bar B and the inertial velocity of the point P. Now you can see that the way this problem is set up is that it gives you dimensions 0.4 in this horizontal direction, 0.4 in the vertical direction, and 0.8 in this horizontal direction, which really gives us a snapshot in time. But instead of solving this only for the snapshot, we're going to develop a general expression for the velocity of point P and then plug in our numbers to then get that at that snapshot in time. And the advantage of doing this is that in dynamics, we're interested in not just a snapshot, not just a single state of the system, but we're interested in being able to solve for the kinematics over any state in any configuration. So the first thing we need to do here is redefine the problem a bit. Let's define a length 1 and a length 2 that correspond to the length from O to O prime and the length of O prime to P. In addition, we'll define the angle theta as being positive counterclockwise from the horizontal direction to link O to O prime. We're now ready to apply our reference frames to the problem. The first reference frame is the inertial reference frame, and we define it with as E1, E2, and E3 with an origin of O. E1 is defined as along O, O prime when theta is equal to 0, E3 is out of the plane, and then E2 is the cross product of E3 and E1. Our second reference frame A, is attached to bar A, and so A1 is along O, O prime, A3 is equivalent to E3, and then A2 is the cross product of A3 and A1. Our last reference frame, which is attached to bar B, is made up of the basis vectors B1, B2, and B3, where B1 is defined as along O prime P when the angle phi, which we've introduced, is 0, and then B3 is the same as A3 and E3, and then B2 is the cross product of B3 crossed with B1. We have two transformation tables for this problem. We defined our A reference frame with respect to the inertial reference frame, so our first transformation table relates E1 and E2 to A1 and A2. In a similar manner, we defined the reference frame for bar B with respect to the inertial reference frame. Now it was with a clockwise angle, positive clockwise angle phi, and so our transformation table looks different, in which the negative sign is relating B1 to E2 instead of the negative sign relating B2 to E1. And for the angular velocities, our angular velocity of reference frame A as observed in the inertial reference frame is theta dot in the A3 direction. In the book, we call this omega A in the A3 direction. And then the angular velocity of reference frame B as observed in the inertial reference frame is negative phi dot in the B3 direction. And in the book they call this just omega B in the B3 direction. So we'll come back to this notation. We'll use this notation as we work through the problem so we can stay consistent with what we see in the example in the book. Alright, so let's talk briefly about the constraints in this problem. We have point O that's fixed, and so this rod O prime is fixed at that point, and then O prime is connected to O prime to P. Now the main constraint that we're going to be applying that's geometric here is that P is constrained to move along a horizontal direction that's equivalent with O. And so this gives us both a position constraint for point P as well as a velocity constraint for point P. Let's deal with the position constraint first. Because P is always vertically aligned with point O, the constraint we apply is that the position vector of P with respect to O dotted with E2 is equal to 0. And looking forward to the velocity constraint, this is also going to give us that the velocity of P with respect to point O, as observed in the inertial reference frame, dotted with the E2 direction will also be 0. So we'll create our position vector, which is rp with respect to O, is the sum of O prime with respect to O plus p with respect to O prime. We write this in our body fixed bases as L1 in the A1 direction plus L2 in the B1 direction. Transform this to the inertial basis by substituting in the expressions for A1 and B1 from the transformation tables. Then collect the terms in the E1 and E2 directions. And now with it collected, we can now apply our constraint, in which our position vector of p with respect to O dotted with E2 is equal to 0. So we take our E2 term and set that equal to 0. This gives us the expression where L1 sine theta minus L2 sine phi is equal to 0. And so we see here that the angle phi is dependent upon angle theta. They're related to each other because L1 and L2 are constants. And so now we've mathematically stated that this is a 1 degree of freedom system, because as the angle theta changes, which is what the input is into the system, or the angular velocity theta dot omega a as we've defined it, then the angle phi is naturally going to change as well. And so in its most useful form for what we're doing, we're relating the angles to each other. So let's define phi in terms of theta. So phi is equal to the inverse sine of L1 divided by L2, so it's this ratio of the lengths multiplied times sine theta. Now notice here that you could have easily determined this through the geometry of the problem by defining theta there, defining phi here, and using some trigonometry on, perhaps relating this common edge of those two triangles. However, that's not very systematic. That's all using intuition. And recall that in this class we always want to use systematic ways. And so this is the most systematic way, which will keep you out of trouble, and it's worth going through this mathematical procedure to determine this expression. Now that we've dealt with the position constraint on point P, let's apply our velocity equations and then apply our velocity constraint. We define our velocity of point P as the addition of the relative velocities, where we have the velocity of O prime with respect to O, as observed in the inertial reference frame, plus the velocity of P with respect to O prime, as observed in the inertial reference frame. So let's write each part of these separately and then add them together. The velocity of O prime with respect to O is going to be 0, because we know that the velocity of O is 0, plus omega a as observed in I crossed with the position vector of O prime with respect to O. This is equal to omega a in the A3 direction crossed with L1 in the A1 direction, which gives us L1 omega a in the A2 direction. Similarly, the velocity of P with respect to O prime, as observed in the inertial reference frame, is omega b, as observed in I, crossed with the position vector r of P with respect to O prime. This is equal to omega b in the B3 direction, crossed with L2 in the B1 direction, which gives us L2 omega b in the B2 direction. So adding these two parts together, the velocity of P as observed in the inertial reference frame is equal to L1 omega a in the A2 direction plus L2 omega b in the B2 direction. So we have here an expression for the velocity of P, which we've taken into consideration that point O is fixed and that point O prime is shared between the two lengths. However, we haven't applied our constraint yet, in which our velocity of point P is only in the E1 direction. So let's write that constraint equation, which we said the velocity of p as observed in the inertial reference frame dotted with E2 is equal to 0. Another way to write that is that the velocity of p as observed in the inertial reference frame is equal to a scalar v sub p only in the E1 direction. And so to apply this constraint to our equation here, we now need to put this in the basis, not A2 and B2, but we need to connect our bases in the E1. So we're going to convert this expression into an inertial basis. So substitute expressions for A2 and B2 from our transformation tables into the velocity equation for point P as observed in the inertial reference frame. And then collect our terms so that we have an E1 expression and an expression for E2. Then we'll set this equal to that constraint, which is V sub P in the E1 direction. Now equate our terms on each side of this expression so we have two scalar equations. The first equation is negative L1 omega A sine theta plus L2 omega B sine phi is equal to speed of P, and then the second L1 omega A cosine theta plus L2 omega B cosine phi is equal to 0. And so we now have three equations and three unknowns. Our three unknowns are our speed, we don't know omega b, and we don't know phi. But we take care of our speed and omega b in this equation, and then we relate theta to phi in our position constraint equation from earlier. So now let's solve. When we're given omega a, we know the lengths of each rod, and then we're solving only for when theta is equal to 45 degrees. So first we can take one of our scalar equations and solve for omega b as a function of omega a. And so it's negative L1 over L2 multiplied times the cosine of theta divided by the cosine of phi multiplied times omega a. When we calculate that when theta is equal to 45 degrees, phi is equal to 26.595 degrees. And we substitute this and the lengths into the equation, and then find that omega b is equal to negative 0.501 omega a radians per second. Now there's a little bit of round off error here because we got 0.501, and that comes from converting into those links that we did at the very beginning of the problem. But we see here that our angular velocity of rod B is half the magnitude of our angular velocity of the link A, or rod A, and it's going in the opposite direction. And this negative sign should also make sense because as link A rotates counterclockwise, because P is constrained horizontally, link B is going to rotate in the opposite direction. It'll be clockwise. So finally, let's solve for the speed of P. And to do this, we have our expression from our scalar equation where we have the speed of P is a function of the lengths of each rod and the angular velocities of each rod, or angular speeds of each rod, and the position. So you can see that the speed is a function of the state. We make our substitutions with our known variables, and then this gives us an expression in which the speed of point P is completely a function of omega A. And then when we simplify this, the speed of P is equal to negative 0.601 omega A. So it's a proportion, or so we can express that as a proportion of the angular speed of rod A. So let's take a look and make sure that this makes sense. We have a negative sign here for our speed of point P. And we defined our velocity of P, recall, as the speed of P in the E1 direction. So that would mean that a positive speed would be going to the right. And so here, if we have a positive angular input for rod A, or for the angular speed, then it should move point P to the left, which would make this a negative speed, so pointing the velocity in the negative E1 direction. So our expression makes sense. So to wrap up, what we've done is we've developed three scalar equations which relate the angular speed of rod A to the speed of point B, as well as the angular speed of rod B. And so with this information, we can solve for the state of the system at any point, knowing just minimum information in this 1 degree of freedom system. Now I encourage you to look at the way the example in the book is worked, because they come up with the answer in a lot fewer steps than we see here. However, there's an enormous constraint on that, simply because that's only valid for this point in time. The expressions that we developed here are going to be valid for any point in time. And so if we only look at a snapshot or an instantaneous position in time, that doesn't help us design much, because we can't play with we can't mess around with the lengths of the rods, we can't mess around with different velocities or different configurations. But it is important, let me say, it is important to be able to do that, because on the Fundamentals of Engineering exam that you'll take when you're a senior, all of the problems, you don't have time to work 30 minutes through a problem. Instead, you need to be able to come up with the answer quickly. And the way that they demonstrate this in the book should just take a matter of a few minutes.